I want to talk a little bit about the performance and the way we achieved it, because it's kind of neat and something that is completely new in the case of Stoke. Basically, the simulation itself is multi-threaded on pretty much all the CPUs that you have, unless you're limited. So if you go and select the Stoke and take a look at the settings here, right now it says that you want caching threads to be unlimited. 0 means don't do anything. And if you click here, you can set it to any number. You can try to set it to more threads than you have, but it won't do it. If I try to set it to 12, it sets it to 8. Because on my machine, I have 8 threads. I have 4 cores with hyperthreading. So you cannot set it to more than 8 in my case, but if your machine has more, you can set it to whatever you want. The idea here is that when you're simulating, it always uses all the cores. It's all 8 will be used if you have them. That's why my microphone is probably being affected when I'm simulating during the presentation. But during that simulation, it's also saving. And this number here tells the system to reduce the number of threads used for saving to less than the number of threads that you actually have. Because, as you're going to see, the saving is happening in the background while you're doing other things, and you might want to leave more power for the other things that you're doing. But by default, it will actually simulate on 8 and then save on half of that. So on 4, it will be saving during the simulation by default, and when it finishes simulating, it will start saving on 7 threads instead of 8, so it leaves me 1 for working, and the other 7 are busy saving files. So the reason it's fast is, as I mentioned, we create a acceleration structure from the geometry when we're emitting, so we are really fast at accessing all the channels of meshes, and you can distribute in volumes and surfaces and vertices and all the stuff and get data from there. We can access our own channels from PAT objects, so that's also pretty much 0 overhead to get channels from another particle system while emitting. Then we have the caching of data to memory. You probably notice that each time I'm simulating, there is a counter here that tells me how much memory I'm using, and I can actually reduce that amount by caching every end frame. And in that case, less data will be written to disk and less data will also go to memory. I'll simulate only into memory, and you see that it's actually creating a green line only every 5 frames. But if I stop this and play back, now we're using only 59 megs instead of the 300 that we had before. But the actual simulation results looks very similar because we're doing cubic interpolation within every 2 frames, so the velocities are very plausible and very close to the original. Only the emission might happen 5 frames later in this case because we shifted the time.
So you could ostensibly render like that. You could do every nth frame, and then
I can do what I can do is it's very important here to distinguish between we are actually saving every 5th frame to disk, which is not so good. That means I'm actually not sure. It looks like I didn't delete the previous ones because I still have every frame here. But no, I didn't save to disk. That's why. If I save to disk while simulating, let's go and take a look. But basically, after I do this for a few frames and go back here, you see that I have only frame 4, 9, 14, 19, and so on. Every 5 frames have been saved. And that means that if you load that in a PLT loader, currently Krakatoa will have troubles in between, because the PLT loader doesn't have interpolation from farther frames than the next one. We should probably look into that. But you can use Stoke itself. So what happens is, if I would, for example, go and say, this Stoke, I'm going to clear the cache, reset the memory cache. So memory cache is gone. I can check this one and check it again. And it loads it because it's on disk. Every time I load the scene, the PRTs get loaded and the data is there, and I can play back exactly the same simulation that I just made. And if you run the Stoke itself in Krakatoa, it will interpolate correctly in between. That means you can save a lot less PRTs to disk. You can load much less memory. You can scrub something that looks very plausible, and you can render in Krakatoa something that's very plausible as long as using Stoke itself as the source in Krakatoa, instead of, if I switch to Krakatoa, latest Krakatoa 218 has this Stoke button here, and if I go and start rendering that, it will probably render. I would have to switch to probably additive mode in order to do something, and Stoke is checked, and I have 100,000 particles. It's probably nothing exceptional, but see, those are the particles. I'll add some motion blur with probably 8 samples and 360. A little bit blurred, and I can go lower with the density. Here you go. So I can go to frame 17, that was never saved, only 14 and 19 was saved, and still any frame that I try to render will render in Kryktor. And
Okay.
that way
cool.
you're saving a lot of this space.
Yeah, yeah.
Yeah. In fact, you can take the Stoke-based object, remove the whole freaking UI that's on top of it, and I did that once. I created my own PRT loader that has the abilities of Stoke, but it's just reading a single PRT sequence from disk, caches it in memory for very fast playback, and you can render any frame with interpolation and do all the graphing stuff that you can do normally, change which frame is loaded and keyframe the use graph and so on. All the features that PRT loader already has, but with the added bonus of better interpolation and faster memory caching. So we'll probably have a PRT loader in the future for Kryktor that behaves more like Stoke, because we learned a lot from this.
Cool.
Good. So and now we're going to the actual caching part to talk about it, because I'm going to switch this back to cache every single frame. I'll be, no, I mean, the number of particles is exactly the same as it was, but let's watch what is happening inside that folder while we are saving. I'll hit simulate and go back here, and you see that currently I have set 2 threads to be used for saving, and 2 threads are actually saving. I'll stop this, and I'll go, and I'll say I want it to be unlimited, 0. I'll resume, and let's see, it's saving now 4 at once. And during the simulation, because I said half of the available threads will be used in order to affect the simulation timing. So it's simulated, and then if I had a lot more particles, which I can do by going here and saying, I'm going to disable this option, I'll start emitting thousands of particles on each frame in order to create a lot, no, about 10,000. It will create 1,000,000 in the end, and it will be really slow. So if I start simulating now, same story will happen, that we are saving 4 or 3 at a time, up to 4. Sometimes 1 disappears because it's done, and lots of particles are coming together. And then let's see. It actually finishes really fast, so you cannot really catch it when it's saving on 8 threads at once. Actually 7 in this case. But here in the listener, it tells you what it's doing. It says flushing cache using 7 threads on 8 cores. It just didn't have enough data because I'm simulating very few particles, relatively speaking. If I continue adding more particles, it will probably get even higher. It starts putting stuff in the buffer. So it simulates, but it doesn't really use the memory so much for the caching. It's more for intermediate buffer, so it can save in between. And if I stop here, I don't know, it will probably dump so fast that we won't notice. Anyway, let's take a look how what the logic is behind this. So in the case of Stoke with actually, in the case of the particle flow with film effects and Kryktor, everything is sequential. So you take the particles from particle flow. Particle flow emits the particles, gets the velocities from film effects, advects each particle on 1 core, and then Kryktor comes and saves the particles 1 file at a time. Because the file is zipped, most of the time actually goes, it's CPU based, so it goes into compressing. The I/O is, we measured it, and it's insignificant compared to the CPU load. That means that most of the time you are loading 1 CPU just to zip stuff. In fact, we're using 2 CPUs in order to be faster. There are buffers that are being swapped back and forth. The one is reading from pflow, the other one is zipping in the background, and then they switch or something like that. And the same with reading is similar. So it's relatively fast, but it's still single thread used to do the zipping, the saving to disk. In Stoke, though, everything is parallel. That means we emit particles and started vectoring them. We load the velocities from film effects, and each particle can run on a separate core, or a bunch of particles, like chunks of particles are being advected on all the cores that we have. That already gives us a significant, probably 6 to 7 times faster simulation, probably even 10 times faster than particle flow could do the same thing. Let's say we're reading FumeFX data and simulating in pflow and in Stoke. Just the pure simulation time is approximately 10 times shorter in Stoke. The trouble is that if you're saving on a single thread, the saving time will eat all that advantage, because saving takes a lot longer than the simulation. And that's why we actually multi-threaded that part too, to save multiple files in parallel. And we're saving them in the background, so the moment the simulation finishes, you're free to do other things, and the saving continues on a background thread without blocking Max. This is what it looks like in graph representation. pflow simulates on a single core, finishes the data, passes it to Krakatoa, that saves to PRT, then the next frame gets simulated and saved to disk, and next and saved to disk. So up to here, you got 3 frames saved to disk. In Stoke, the simulation itself, it's faster, like the advection, because it runs already in multiple threads. And when one frame finishes, it triggers a background thread that actually saves that file. And when the next frame finishes, another thread can start saving that file. And when this one finishes, I can have any number of threads here, 4, 8, depending on what cores you have on your machine. But if I'm simulating really fast, I can pretty much keep up with the simulation and dumping data in parallel threads to disk. So when the simulation finishes, it's already faster, and all the saving is shifted in the background. So even if it's not done, I'm free to do other things. This is what we call the synchronous cache, and it's completely new in Stoke, and we don't know of another tool inside of Max actually doing anything like that, because multi-threading in Max is a tricky business. So if we take a look at the graph where we actually benchmark the whole thing, you're going to see that the total simulation time of particle flow is for 100,000 particles per frame, which creates 10 million particles on the last frame over 100 frames. It creates 15.2 gigabytes of data in PRT files. That was run on a Quad Xeon. That's not the machine that I'm currently running, but my other machine. My current one has only 12 gigs, but that one had 32, and I was playing a little bit more with memory. We'll see in a second. So the way I simulated this was I went to the last frame and tried to render the frame in Krakatoa, and then Krakatoa told me how long it took to get that frame. So this 420 seconds is the actual pre-roll time to get to frame 101 and simulate all the particles from the beginning, all the emission and all the advection through a FumeFX. So you're going to see that the simulation time of Stoke itself is 40 seconds, which is already 10 times faster than the simulation time in pflow. And that's just based on the multi-threading and the better advection algorithms that we're using. Actually, this time here is using half frame step, because that's the default settings of pflow. In order to get good motion, you're using half integration step. If you go to one step, one frame there, it's going to be half the time, so about 200 something, about 200 seconds. It still will be 5 times faster than that. And we're not doing any like subframe interpolation in this case, because our integrator is slightly better, and it just produces smoother results without having to do too many subframes. You can do it, but we didn't have to. And then comes the saving time. And when you add the, I call it flush cache time, but that's pretty much the time after the simulation finished, from the beginning of the simulation until the last frame was written to disk. It took 1,549 seconds to do it with pflow, and it took 1,093 on a single core saving. That means that's the worst case scenario in Stoke. And this is what we had in the very beginning of our development. We are saving on a single thread, and we were 10 times faster to simulate, but only 1.5 times faster altogether, because the saving was so slow. So we said, okay, let's shift it to the background and make multiple threads and see what will happen. And when we did that, it turns out that we start adding cores, and the time goes down and down. And with 4 cores, we are already 3.5 times faster than 1 core simulation in Stoke, and 4.9 times faster than pflow itself, including all the saving. And that's already great, because imagine something that is taking half an hour or a whole hour to process, and you do it in 10 minutes or something. All the and what's even more interesting is, since it's a background thread, the actual simulation time is only 50 seconds, of between 40 and 90 seconds, depending on how many threads you're using. That means after those 40 seconds, or after those 50 seconds, or after those 90 seconds, Max is free for you to work again. The saving goes back into the background, might take 10 minutes. If you don't like the result, you just hit simulate again, and the other process stops, and you save new files. But if you like the result, you just let it run in the background and do something else creative. That means if you compare this time, those about 50 seconds, compared to those thousands of seconds, your benefit, the actual simulation time where you cannot do anything but wait for the system, it's very, very short, and it's probably 40 times faster than what you would do with pflow. And that's why we think that Stoke is worth it, because if you're doing that integration on a single thread with pflow, with FumeFX driving Krakatoa day in and day out, because that's your job and you're doing it really often, we believe that we can save you hours per day. And you can be more productive, you can tweak settings, hit simulate, watch a few frames, saving starts in the background. If you like it, you resume. If you don't like it, you change parameters and sim again. And after a few seconds, you're still free to continue working, and the saving continues in the background. That's not all. Memory doesn't really make much difference. I mentioned that I had 32 gigs of RAM there. This simulation that I'm talking about with 10 million particles needed 19 gigs of RAM to fit completely in memory for playback. So I could scrub the time slider as much as I wanted. But my current machine that I'm using here has only 12 gigs. My laptop has 8, and some laptops have 4, even 2. So we wanted to know what happens if you don't have the memory. Turns out it doesn't matter. Because the big difference will be how long you have to wait until you can start working with Max again. So let's say you have enough memory. You start simulating. Fastest example with all 8 threads actually working. 90 seconds is the time until you can start being interactive with Max again. 144 seconds more is the flushing of the cache after that point, where it's saving in the background, but you're still working in Max on other things. So the total time is 237 seconds approximately. That is the time that we saw here. Now, if you start reducing the amount of cache, that means the caching memory here can be reduced to any number. You can go to 1,000, you can go pretty much to 0, and it will still simulate, but use only as much memory as you need to fit the largest frame of your simulation. All the previous memory is dumped from the memory, and if I start simulating here, you see it's actually blue. Shows I have the data on disk, but I don't have it in memory right now, so don't ask me about it. If you start asking me for it, I'll load it. So I can go back a frame, and that frame will be loaded from this, but everything else gets dropped. And if I go and increase the cache again, if I start moving around, the blue will turn green, and each frame will be loaded and kept in cache. So this way, I can actually simulate without really using any memory. And what happens in that case, when you come around here, when I said limit will be only 12 gigs, what happens is that I need 19 gigs to fit all the simulation. Simulation passes in 90 seconds, is done, but there is no memory to actually keep that data, so the simulation has to stop and wait for the saving threads to release some memory. And that's why instead of 90 seconds, we went to 190 seconds waiting time, but the actual saving time is reduced by 100 seconds because the saving is happening while the simulation thread is waiting. So simulation gets longer, but saving doesn't really change. It gets shorter, and the total time is pretty much the same. No matter how much memory you throw at it, even if you remove all the memory and say 0 limit for buffer, just simulate and save, you're still going to actually get the same simulation time. It's just you'll be interactive much later. You'll have to wait until the whole process is done before you can start using Max again. The more memory buffer you have, the earlier you'll go back to work, but your from the moment you hit simulate to the moment the last PAT was written to disk, exactly the same. It balances itself. It's just how much memory you give it to speed up the return to interactivity. So we find this really amazing and really cool, and you can use your laptop, whatever cores you have on it, and if you have only 2 gigs of RAM, if you can launch Max, you'll probably be able to do some Stoke simulation. Now, you still need the memory to fit 10 million particles in memory, but that won't be that much.